Hey guys, welcome to Intellipaat. In today's session, we are going to learn about decision trees. First of all, let me tell you why you should be interested in learning about decision trees. Decision trees are schematical and geographical representation to all the possible solutions of a decision-based problem. It is used to make smart decisions. Not only is it very crucial in the field of data science, but it is also very crucial in the field of machine learning, where it is used for predictive analysis. So if you are interested in any of these fields, you must stay tuned till the end of this video. Now before we go forward, do subscribe to Intellipaat's YouTube channel so that you never miss out on any of our upcoming videos. So first of all, we are going to learn what is a decision tree with the help of a real world example, and then we are going to learn how to build a decision tree. Also guys, if you are interested in becoming a certified data science professional, then do check out the data science course offered by Intellipaat. You can find the course link below in the description box. Now without any further delay, let's get started.
So decision tree is basically a technique or a data structure which we build that helps us in making decisions. So here all the internal nodes represent a test condition on an attribute, and all the leaf nodes are the categories into which the data is divided. So let's take an example to understand this better. So let's say you are the manager of a telecom company and you want to understand what are the factors which make a customer to churn out. So you decide to build a decision tree. Now, this decision tree will give you a series of test conditions. So here the root node is gender. That is, the first condition would be decided by the gender column. So if the customer is male, then we'll further determine what is the duration of his tenure. On the other hand, if the customer is female, then the next test condition would be on the basis of monthly charges. So let's say the customer is male. Then we'll check his tenure, and if his tenure is less than 30 months, then he will churn out. And again, if his tenure is greater than 30 months, then he'll stick to the same company. And this is the final prediction given by the decision tree. So similarly, if you get a female customer, then we will have to check her monthly charges. So if her monthly charges are greater than $80, then she'll churn out. And if her monthly charges are less than $80, then she'll stick with the same company. So we are exploring a series of alternatives to reach a particular decision point. Now that we've understood what is a decision tree, let's look at the types of decision trees. So a decision tree can either be a classification tree or a regression tree. So a classification tree is used when the response or the target variable is categorical in nature, and a regression tree is used when the response variable is numerical or continuous. So let's say we have a dataset A and there are n records in it. Now what I'm going to do is draw samples from this dataset. So this actually will be sampling with replacement. That is, I'll take one record from dataset A, take note of it, enter the same sample in dataset A1, and then put the record back to where it came from. And I will repeat this process n times so that there are n records in dataset A1 as well. So what you need to keep in mind is that out of these n records in A1, some of them might have come twice, thrice, or even several times over, while some records from A might not have made it at all to A1. So I've created A1 like this, okay? And then I'll go ahead and create multiple data sets the same way. So I have A1, A2, A3 till A of X. And each of these have the same number of records as A. And the X over here could be anything. Let's say 100, 500, or even 1000. So from just one data set A, we are able to create multiple data sets for our advantage. So just for our sake, let's say dataset A has 1000 rows and the value of X is also 1000. So this would be 1000 into 1000, which would give us 1 million rows. That is, from just 1000 rows of data, we were able to get 1 million rows. Now what we'll do is, for each of these X data sets, we will fit one decision tree each. So we have X decision trees coming from X data sets. So now we have a group of trees, or in other words, what we have here is ensemble of trees. Now let's say a new record Ri comes away. Then we're going to pass this record to each of these X trees, and we're going to get each tree's prediction on what class this new record is going to represent. And since we have X trees, we will get X predictions. That is, if let's say X was 500, we would get 500 predictions. Similarly, if X was 1000, we would get 1000 predictions. Now to get the final prediction, all we have to do is select that class which would have the majority of the votes across all of the predictions from individual trees. So what we are really doing here is aggregating the predictions across all these trees. So guys, this is the concept of bagging.
Just a quick info guys. If you're interested in becoming a certified data science professional, then check out the data science course offered by Intellipaat. You can find the course link in the description box below. Now let's continue with the session.
So we will use the same example for bagging and understand where the difference comes. So again, we have this dataset A and there are n records in it. Now what I'm going to do is draw samples from this dataset. So this actually will be sampling with replacement. That is, I will take one record from dataset A, take note of it, enter the same sample in dataset A1, and then put the record back to where it came from. And I will repeat this process n times so that there are n records in dataset A1 as well. So what you need to keep in mind is that out of these n records in A1, some of them might have come twice, thrice, or even several times over, while some records from A might not have made it at all to A1. So I've created A1 like this. And then I'll go ahead and create multiple datasets the same way. And each of these have the same number of records as A. And the X over here could be anything. Let's say 100, 500, or even 1000. So from just one dataset A, we are able to create multiple datasets for our advantage. So just for our sake, let's say dataset A has 1000 rows and the value of X is also 1000. So this would be 1000 into 1000, which would give us 1 million rows. That is, from just 1000 rows of data, we were able to get 1 million rows. So till now the process is same as bagging. So this is where the difference comes. Now what we'll do is for each of these X datasets, we will fit one decision tree, but the process of building the decision tree changes over here. So let's say this A1 dataset has 10 independent variables. Now when it came to bagging, we considered all of these 10 independent variables to be a choice for the split candidate. But what happens in a random forest is, each time a node is being split in a decision tree, not all 10 columns will be provided to the algorithm. This is important, so I am reiterating this guys. So each time a node is being split in a decision tree, not all 10 columns will be provided to the random forest algorithm. So now the question arises, what will be made available to the algorithm? So only a random subset of these 10 columns will be available to the algorithm. So let's say I want to split this root node. Now instead of providing it all the 10 columns, only a subset of these columns will be provided. So let's say 3 columns. And it could be any 3 out of the 10. And with those 3, the algorithm goes on to split the node. And similarly for the left node over here, it is again going to be provided with a random set of 3 variables. So it's not necessary that the left node should get the same 3 variables. It can be a different set of 3 columns altogether. So whenever we are splitting a node, it is given a random set of m predictors from the entire predictor space. And the reason this is done is to make each of these X trees very different. So let's compare bagging and random forest. So in bagging, all of the trees had the entire predictor space available to them. So the eventual trees which you would end up building are going to be very similar to each other. And in the case of random forest, we bring in this randomness with respect to the columns provided. That is, only a random set of columns are provided from the entire predictor space. And that is why the set of decision trees which you would get would be quite different from each other. And now after this, the steps are pretty much the same when compared to bagging. So let's say a new record Ri comes our way, then we are going to pass this record to each of these X trees. And we are going to get each tree's prediction on what class this new record is going to represent. And since we have X trees, we will get X predictions. And to get the final prediction, all we have to do is select that class which would have the majority of the votes across all the predictions from individual trees. So guys, this is the concept of random forest. Today we'll actually be using 3 different packages to build decision trees. We'll be using tree, we'll be using rpart, and we'll also be using the party package. So this is ctree function from the party package. So we'll learn 3 different functions to implement the decision tree model. So first we'll start off by loading this package, library of ISLR. And now this package basically has this car seats data. So you would have to say data of car seats. You'd have to load this data. Now let me have a glance at this. So this is our first data set, which basically has sales of different cars. Now let me go to the help and show you the description of this. Right, so this is a simulated data set containing sales of a child car seats at 400 different stores, and these are the different columns. So sales is unit sales at each location, comp price is price charged by competitor at each location. This is community income level, this is local advertising budget, population and size, price company charges for car seats, and so these are the rest of the columns. So what we'll do is first we'll start off with classification. So as I had told you guys in yesterday's session, a decision tree can be used for both classification and regression purpose. So on this data set, we'll be basically trying to classify something. So our first task would be to take this sales column and divide this and actually convert this into a categorical column. So wherever the value of sales is equal to or less than 8, we will tag that as low. And similarly, wherever the value is greater than 8, we will tag that as high. So that will be our first task. And since it's a classification task, we would need a categorical column. So let's do that. So we will use this if else function. So what we are doing is we are taking this sales column from the car seats data set, and wherever the value is equal to or less than 8, we'll say it is no. So basically it is not a high sales car, and wherever it is greater than 8, we'll say yes. So let's go ahead and create this new variable. Yeah, so I'd have to actually convert this into small c first. So I'm basically taking this data set and storing this into a new object. So this is capital C, this is small c. That's pretty much the only difference over here. And now I will take the sales column, and wherever the value is less than 8, I will tag it as no, and wherever the value is greater than 8, I'll tag it as yes, and I will put that result in the object high. Now I'll create a new data frame which consists of all the columns from this car seats dataset, and I will add this new object to it, and I will store it back to car seats. So view of car seats. Right. So over here we see that we have added this new column, this yes and no. So yes basically indicates that the sales value is greater than 8, and this no value indicates that the sales value is either equal to or less than 8. So now right, we have a data set with us, so it's time to build the model, and we'll start off with the tree function actually. And to use the tree function, you would require the tree package. So let's load this. Yeah.
How the high column already there, or it's created here?
No, I am creating that new column. So let me actually show you the original data set. View of car seats. So this is our original data frame, which does not consist of the high column. So what I'm doing is I am taking the sales column, and from this, wherever the value is equal to or less than 8, I am tagging it as no, and wherever the value is greater than 8, I am tagging it as yes. And that result, I will store it in a new object and name that object as high. So this will basically be our new column. So I am adding that new column into the car seats data frame in our original data frame, right? So I'll store the result back to car seats. Able to follow this?
Yeah.
Right. So we have our data set with us over here. Now it's time to build the model.
Just a quick info, guys. If you're interested in becoming a certified data science professional, then check out the data science course offered by Intellipaat. You can find the course link in the description box below. Now let's continue with the session.
And to build the model, we will be using the tree package. So library of tree. Now we will use this tree function, and we want to understand whether the result is high or not, or in other words, whether the sales value is high or not on the basis of all of the other columns. So over here, if I want to know with respect to all of the other columns, I'll just put a dot over here. So the dependent variable is high, and the independent variables are rest of the columns minus sales. This is because this high column has been created from the sales column, right? So I'll take all other columns except the sales column. Able to follow this? Why am I removing the sales from the independent variables? And then again, so I'm not splitting the data set as of now. So I've just I'm building this model directly on top of this entire data set. So data will be equal to car seats. Now let us have a glance at the summary of this. So summary of tree dot car seats, and this tells us about the different independent variables and the number of terminal nodes we have and the misclassification error rate. Now let's actually go ahead and plot this. So plot of this tree dot car seats. Now we'll also go ahead and add the text to this. So text, and we'll pass in the same model which you've built. I'll say pretty is equal to 0. Right. So now if I remove this pretty equal to 0, so basically this categorical column which you see, that takes in, okay, let me remove this first. Right. Now let me plot this. So when I'm plotting this, you get the categorical levels as just alphabets. Now, if I want the categorical columns with respect to their names, I would have to give in pretty equal to 0. So I will delete this from over here. Right. So we will get the actual categorical columns over here. So now let's actually have a look at this and understand what is happening. So we want to see if the sales are high or not. So the first split point is based on the shelf location column. So this is the column, and this determines the first split. So over here, if the value is either equal to bad or medium, then we go on to the left side. On the other hand, if the value is equal to good, then we go on to the right side, right? So let's go to the right side. Again, we'll check if price is less than 135. If price is less than 135, then we'll come to the left side again. Again, we'll check if price is less than 109. So if price is less than 109, then the value of sales will be high. Similarly, this does the same thing over here. So this is how we can plot the decision tree which we've just built. Right. Now, so this is the model which we've built on top of the entire data. Now what we'll do is we'll divide this data into train and test sets and build the model on top of the train set and predict the values on top of the test set. Right, so again, I'll be using the same package, CA tools, which will give me the sample.split function. I'll load this up. So let me set a seed value first so that even you guys get the same value. So I'm setting a seed value of 101. I'll use the sample.split function, and the split criteria over here is the high column, and the split ratio is 0.65, which basically means that 65% records go into the training set and 35% records go into the testing set, and I store this in split tag. Now let me use the subset function, and with the help of the subset function from the entire car seats data set, wherever the split tag value is true, I'll store that in train set. Similarly, from this entire car seats data set, wherever split tag value is false, I will store that in the test set. So we have our training and testing sets ready. Now we'll go ahead and build the model on top of the training set. So again, we'll be using the tree function, and again the formula would be the same over here. High is our dependent variable, and all other columns except the sales column are the independent variables. And we are building this model on top of the train set this time.
Hey, Barney, I just lost you. Split tag is equal to true and false. Where did that come from?
Yeah, okay. So I'll start from this. So this sample.split function takes in two parameters. First is basically the column which we want to split into two parts. And since we want a dependent variable to be high, we take this as a split criteria. And the split ratio is basically the percentage of split. So it will basically give us true or false values. So 65% of the observations have the true label, and the rest of the 35% observations have the false label. And I've stored that in split tag. Now let me just print this out. Split tag. So I just have a bunch of true and false values over here, right? So from this bunch of true and false values, what I'll do is from the entire car seats data set, wherever the split tag value is true, I will take all of those records and store them in the train set. Similarly, from this entire car seats data set, wherever the split tag value is false, I will store that in the test set. So here for the first record.
Yeah, that's fine. That's fine. I understand that part. So when we do this split ratio and it stores in split tag, does it assign it as true or false with 65% ratio?
Yes. So basically the division is 65-35. 65% of the records have true, 35% of the records have false. And then we'll use this true or yeah.
All right.
So is everyone able to follow this?
Yeah.
Right. So yep, we've made the split tag, and now I'll use the subset function, and from the entire car seats data set where split tag is true, I'll store in train. Similarly, from the entire car seats data set where the split tags is false, I will store that in test. So we have training and testing ready. Now it's time to build the model on the training set. So again, the function is same. We'll use the tree function, and the dependent variable is high, and the independent variables will take everything except the sales column, because this high column is basically we've made this high column from the sales column, so minus sales, and we are building this model on top of the train set, and we'll store this model in tree.carSeats. I'll hit enter. All right, now let me have a glance at this plot. So I will build a plot again. Right. So this time we see that the split criteria is determined. The first split criteria is determined by the price. So if price is less than 90, then we go to the left side. And if price is greater than 90, we go to the right side. So this is basically the entire decision tree which we have over here. So we have built the model. Now let's also go ahead and predict the values. And to predict the values, we will be using the predict function, and this takes in three parameters. So the first parameter is the model which we built. Second parameter is the test set, because we want to predict the values on top of the test set. And third parameter is the type, so type of prediction. So type of prediction is class. So we'll basically get the direct result over here. So the class is basically yes or no. And again, we're storing this result in tree.pred. Right. So we have also the predicted values. Now I will build the confusion matrix. So this confusion matrix and the actual values come from this test $high. So these are the actual values, and these are the predicted values which are there in tree.pred. So this gives us a confusion matrix. So this value basically indicates that out of the actual values which are no, out of them we classified 68 of them correctly. And this indicates that out of the actual values which were no, we incorrectly classified 15 of them as yes. And this 18 basically indicates out of those values which were actually yes, we incorrectly classified them as no. And these 39 are those observations which are actually yes, and we correctly classified them as yes. So basically this left diagonal indicates all of the correctly classified observations, and this right diagonal indicates all of the misclassified observations. And to get the accuracy, we will divide this left diagonal with respect to all of the observations.
Just a quick info, guys. If you're interested in becoming a certified data science professional, then check out the data science course offered by Intellipaat. You can find the course link in the description box below. Now let's continue with the session.
So that'll be 68 plus 39 divided by 68 plus 39 plus 15 plus 18. And this gives us an accuracy of 76%. Right. And now, as we learned in yesterday's class, that we have a fully grown tree over here. Now, what we'll do is we will go ahead and prune this tree, and we'll see what sort of difference it makes to the accuracy of the model after pruning. All right. So for that, we'd have to do a bit of cross-validation first. So yesterday also we saw the k-fold cross-validation. So the cv.tree is used exactly for that. So with the help of the cv.tree function, we can do the cross-validation, and this takes in two parameters. First is the model which we built, and next is the function. So prune.misclass is basically saying that we are doing this cross-validation for the purpose of pruning our tree. And this is basically an inbuilt function which does the entire thing in the background, and will store this in cv.carseeds. Now let me just print this out, cv.carseeds. Right. So this is basically the size of the tree. So we started off with one root node, and this kept on increasing. So 1, 2, 3, and then finally we have a tree which has 24 terminal nodes in total. And this is the misclassification rate over here. So basically when we have just one node, then the resubstitution error is the maximum. And when we have all of these terminal nodes, so this is the fully grown tree. So this fully grown tree has the minimum deviation, or in other words, it has the minimum misclassification. And this is the cost associated with each of these different levels of nodes. Right. So this was cross-validation. Now let me also plot this out. So plot of cv.carseeds. Let me zoom this. Right. So over here, what we basically see is, as the size of the tree increases, the misclassification rate till here, it decreases and then it increases again. So initially where there were like 2 or 3 nodes, there was a very high misclassification. So when the number of nodes it reached around 15 or 16, then we had the minimum misclassification rate. And after that, when we kept on splitting, there was actually an increase in misclassification. So what we can find out is the ideal number of nodes would be somewhere around 15. Right. So this is how we basically prune our tree. So what we are doing over here is post pruning or cost complexity pruning. So we've found out that this is a fully grown tree is not the right idea. So let me actually print this out. So this value would be, let's say, around 16. So at 16, this misclassification has increased again. So what I'll do is I will build a model with number of nodes to be 16 over here. So let me set this to be 16, and I'll right. So this time the function which we are using is prune.misclass. So this prune.misclass helps us to prune our tree with the best value, or the number of at max the number of nodes would be 16. and I will store that result into prune.car seats. Right, now let me plot this out. Plot of prune.car seats. Now I'll also add the text for this. Right. So this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So initially we had a fully grown tree, but after that we did a bit of cross-validation, and then we found out that fully grown tree is not a good idea, because that fully grown tree does not give us, so after a certain point the misclassification rate basically increases, so there is no point of a fully grown tree. And then we understood that there's a level which is 16, so that is where we have to stop splitting the nodes. So right, so we have pruned our tree. Now what we'll do is we'll predict the values again with this pruned tree. So let's go ahead and do that. So again, I'll be using the predict function. Again, this takes in 3 parameters. First is this pruned tree over here. Next is the test set. And then we have the type, which is class. I'll hit enter. Now let me build the confusion matrix, and let's see what is the accuracy which we get this time. So 68 plus 40 divided by 68 plus 40 plus 17 plus 15, and this gives us an accuracy of 77%. So as we saw earlier, the initial accuracy was 76%. So let me print out the initial value over here. Right, so this comes out to 68 plus 39 divided by 68 plus 39 plus 18 plus 15, and this gives us an accuracy of 76%. But after that we went ahead and pruned our tree, and then we predicted the values again. So after the pruning of the tree we get an accuracy of 77%. So 68 plus 40 divided by 68 plus 40 plus 17 plus 15, right? So this time we have an accuracy of 77%. So is everyone able to understand how did we do pruning and how did we get a better accuracy after the pruning? So any questions still here? So Walid, the seat value is basically so now when I'm basically building this model, all of you might get different values. So if you want the same values as I'm getting, then you'll basically set a seed value, which will give out the same result. Right, so others?
Bunny, actually, I was clear about the model actually. Regarding the seed, every time I heard like seed will be like, it will give the same data. Like how can you show like how it is going seed? I mean, I didn't understand the seed concept.
There is nothing to it. It's just that when I say set seed and then I give a random value to it, so it could be anything. Right, after this, whatever, so let's say I generate a sample, and right, so now if you set a seed value of 33333 and you use the sample function, even you will get the same values. Or if I do sample again, if I do set.seed and use 33333 and set sample 10,2, I'll get the same value. So basically if I want the same result, then I need to use set.seed. That's pretty much it.
Okay, whenever I'm doing splitting every time, changing the ratio, I need to use the seed again, the same value.
No. If it's like I want to if I want to show this result to someone else, right? So now whenever I'm using the sample function, this will give me a different result every time. But let's say I want to show this as an example to someone else. So I want the sample 10,2 to give me the same result every time. Then what I'll do is I will just set a seed value, and that seed value will give me the same result every time. So set.seed of, maybe I give a random value, 1 and sample 10, 2. I get 3, 4. Again, I set a seed value of 1 and sample 10, 2. I get the same result. So set.seed of 1, sample of 10, 2. I get the same result. Right? So basically, when we want the same result, we will use the set.seed.
Yeah, got it.
There is nothing else to it.
Isn't seed a replacement sample function?
Replacement sample? I'm not following you.
So when we do the sampling, right, there will be something which we can replace the values, so it can be repeat itself, right?
No, we're not replacing anything. It says that if you want the same result, that is when we'll use set.seed.
Okay.
Yeah. So there is nothing which we are replacing over here.
A quick question: when we are doing this kind of classification, right? And when we are doing the test, I mean, accuracy and all of that is good, right? Can I get the, on the basis of my test data, can I get the probability of, I mean, I want to just do a scoring now. Can I do that with this classification?
Scoring on what basis?
See, what we did was the first column that you selected, right? And then you said, okay, greater than 8, less than 8, right? And you classified that as yes, no kind of thing. I want to get a scoring, something on sales, kind of predicting, right? How my sales would be predicted. And possibly on that, I may take another decision. Can I get those sales values predicted?
Yes. So what you're saying is basically, can we do regression with the help of this decision tree? That is what you're asking? That we can. So there is an example. So there is actually an example which we'll be doing with the RPart package. So there we'll be actually predicting continuous values with the help of the decision tree.
Okay.
Yeah. So again, so decision tree is used for both classification purpose as well as regression purpose, right? You can do both with them. So this example on this data set will be doing classification, right? So yeah, we did a bit of pruning and we got this result over here. Now what we'll do is, so we will print this out again and we will actually prune it with a different number of nodes. So we have this cross validation and let me paste it over here. Right. So over here, we took the number of nodes to be 16. Now, instead of 16, we'll say the number of nodes to be 9, and we'll see what is the accuracy when the number of nodes is 9, right? So we'll prune this tree at 9 nodes. So again, all we have to do is set this best value to be equal to 9. So it's the same thing again. We'll use the prune.misclass function. First is the model which you built, next is basically the number of nodes which you want, and then we'll plot this out. So over here we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. And this time again, the first split is on the basis of the price. So if the price is less than 90.5, then it's basically high is equal to yes. So this is the model. Now let's go ahead and predict the values again. So this is what we have to do over here. All right. So again, in this, we'll use the predict function. We'll use the model which we've just built over here. This is the pruned model. And then we are trying to predict the values on test set and type equals class. And then we'll also go ahead and build the confusion matrix. So let's see what is the accuracy this time. So 68 plus 37, 68 plus 37 plus 20 plus 15. So this time we see that accuracy is 75. So the ideal split or the ideal level where we'd have to cut out our tree is when we have 16 nodes. So again, that is why this cross validation is very important for us, right? So this result over here, we see that 9 and 16, right? So 16 is ideal. Again, we saw the same thing when we made a plot of this, plot of CV dot car seats, and over here we saw that this is our ideal value. So this is where there is a jump, right? So till here there is a decrease in the misclassification rate, and when, so after we progress from, after the number of nodes progress from 16 and we keep on splitting, the misclassification rate increases. So 16 is our ideal value. So yep, so this was basically how we can build decision trees with the help of the tree package. So after this, we'll be building decision trees with the party package. So this is just again an alternative to build the decision trees. So let me go ahead and load this package. So has everyone installed this package? A quick confirmation, please.
Yeah, install.
All right. So now for this, we will be using the iris dataset. So let me open up the iris dataset. View of iris. So this time we have a three-way classification. So we'll be trying to classify whether the species is setosa, virginica, or versicolor. So levels of iris dollar species. So we see that there are three classes over here, and this time we'll be building a decision tree on top of this data set to understand whether the class belongs to setosa, versicolor, or virginica. Right. So yep, let's do that. So we have loaded the party package now this time. So till now I've been using the CA tools package, and CA tools package gave us the sample.split function. So similar to sample.split, we also have the create data partition package. So it's basically analogous to sample.split. So create data partition is a part of caret package, and sample.split is a part of CA tools package. So I'll load this caret package. Right. Now I will use this create data partition. So it's pretty much the same thing. So instead of sample.split, it's create data partition, and the split column is species, and the split ratio is 65. So this list is equal to false. So normally sample.split gives us, it gives us a vector, but this actually gives us a list instead of a vector. So we'll say list equals false, and we'll store it in split tag, and again it's pretty much the same thing. So now the sample.split gave us true or false values, but this create data partition gives us the record numbers. So let me print this out, split tag, right? So over here we have the record numbers over here. So now if we have to make train and test from the split tag over here, we'd have to basically pass this in as a parameter inside our data set. So what I'm doing is, from this iris data set, I will be selecting all these row numbers, right? So these row numbers comprise of 65% of the iris data set, and I will store them in the train set. Now similarly, so the split tag contains 65% of the row numbers. So apart from those 65%, so when I put a minus symbol, right, so it's basically all of the records minus the 65% of the row numbers which are present in split tag, right? So which are basically 35%. So those 35% records go into the test set. So this is how we create the train and test set this time. So again, I'm repeating this. So this is basically analogous to sample.split, just a different way to split our data set, right? So this time we have the C tree function, which is a part of the PARTY package, and we'll be building our model on top of the train set, and we want to understand what type of species the flower is with respect to these four columns: sepal length, sepal width, petal length, and petal width. So that is why I've put a dot over here, and I am storing the result in my tree. Now let me also go ahead and plot this over here. So this is the difference between tree and C tree over here. So this time the first split criteria is on the basis of the petal length column. So if the petal length is less than or equal to 1.7, then we classify the flower as setosa. So you see this? So there is almost a probability of close to 1, right? So this probability is close to 1. So if petal length is less than or equal to 1.7, then we classify it as setosa. On the other hand, if petal length is greater than 1.7, then the next split criteria is petal width. And if petal width is less than 0.001, sorry, if its petal width is less than or equal to 1.7, then again we'll check the petal length. And this time, if petal length is less than or equal to 4.8, then it will be versicolor. On the other hand, if petal length is greater than 4.8, then there's around 50% or around 60% probability that it's versicolor and around 40% probability that it's virginica. On the other hand, if petal length is greater than 1.7 and petal width is greater than 1.7, if this is the case, then it is virginica, right? So over here, we are doing a multi-way classification and we are trying to
Little confused here. 1 and 3, right? The splits are same. Values of splits are also same below.
which split?
Box one, right?
Uh,
And box 3, right? The splits are happening less than 0.001, and then it is splitting at greater than 1.7 and less than equal to 1.7. And same thing is happening on the box 3 as well.
Right. So forget about this p-value over here, right? You take these values. So this is the value of petal length. This is the value of petal length. This is the value of petal width. This is the.
Let me ask you another question now. On the right hand side, when you move, right, it's 1.7. Anything greater than 1.7 will go towards the right hand side, right?
Yeah.
Then how can we, after box 3 split again, right? How will you get a value of less than equal to 1.7?
One is petal width and the other one is
This
petal
is
length. So
petal
you started off
length.
with petal
Oh,
length.
okay.
Petal width.
Okay.
Right.
Yeah.
So is that clear?
Yep.
Right. So again, forget these p-values. If these are confusing you, so just forget these p-values. So first, we are splitting it on the basis of petal length. So if petal length is less than or equal to 1.7, then we can be almost 100% sure that it is setosa. On the other hand, if petal length is greater than 1.7, then we will check petal width, right? It's not petal length, it's petal width. So if petal width this time it's less than 1.7, then we'll check petal length again. And if petal length is less than or equal to 4.8, then we can be almost 100% sure that it's versicolor. On the other hand, if it's greater than 4.8, then there's around 60% probability that it's versicolor and there's around 40% probability that it's virginica. On the other hand, if petal length is greater than 1.7 and petal width is greater than 1.7, then again we can be almost 100% sure that this flower belongs to virginica. So what we did over here is a multi-class classification where we are trying to understand whether the flower belongs to setosa, versicolor, or virginica, right? And this model we've built with the help of this C tree function over here. So we've built the model. Now let's go ahead and predict the values this time. So again, I will be using the predict function, but now, so in the previous case, we had said type equals class. So this time, this C tree function, the predict value, the type value, it will be response, right? So these are like the minute differences between these functions over here. So when we used the tree function and we were predicting the values, where exactly is it? Right, so this when we use the tree function and we were predicting the values, the type of prediction we set it to be class. And when we are using the C tree function and we are predicting the values, the type over here will be response. But then again, the parameters are pretty much the same. First is the model which we've just built. Next is the test set on which we are building the model. Next is the type of prediction. So over here, type of prediction is a response, which is pretty much same as class. It says that nomenclature changes when it comes to the C-tree function. And we will store this in mypred over here. So we have also predicted the values. So now let's go ahead and build a confusion matrix. So these are the values where the actual was setosa and has been correctly classified as setosa. So these are the two cases where actually it was setosa, but it has been classified as versicolor. These are the cases where actual was versicolor and it has been correctly classified as versicolor. This is the case where actual is versicolor and it has been incorrectly classified as virginica. This is the case where actual is virginica and it has been incorrectly classified as versicolor. This is the case where actual is virginica and it has been correctly classified as virginica. So again, this left diagonal which you see, these are the correctly classified values, and the rest, so this 2, 1 and 2, these are the incorrectly classified values. So let me go ahead and find out the accuracy. So this time it'll be 15 plus 16 plus 15 divided by 15 plus 16 plus 15 plus 2 plus 1 plus 2, right? So you get an accuracy of 90%, which is very, very good. Now, what we saw in the plot was the split was determined by only petal width and petal length, right? So petal length and petal width. So these are the only columns which are determining the split, and these are the only columns which determine whether the flower belongs to setosa, versicolor or virginica. So that is why what we'll do is we will build another model where we will take only petal width and petal length as the independent variables, because what is the point of including other variables when they are not even a part of the split criteria, right? So let me go ahead and build another model. So again, C-tree, the formula this time, dependent variable is species and the independent variables are petal width and petal length, only these two. So we do not take sepal length and sepal width this time. And again, we are building this model on top of the train set. Now let me go ahead. So I'll delete this first. Now let me make a plot of this, right? So this is pretty much the, yeah.
Yeah. So from as what you said, from that decision tree, you got to know that only two things are getting used, and you did not use the other columns. So is this something how you reduce the number of dimensions which should be there in your model? Is that something which we should use it? If I have 10 variables and if I get a clue from this particular model in saying that you don't require the other variables, I need not use it in any of my modeling. Is it a right way to do it?
Yes, so when it comes to decision trees, this is something you can do. But then again, this is trial and error, right? So again, so whatever, yeah. So again, you need to see what works with respect to the model. So over here, we got a clue that sepal width and sepal length were not part of the split process. So we thought, why not build a model without using these two, right? So it will basically bring in redundancy. So we don't want redundancy. So let's go ahead and build a model and see what the output is. So that is what you do. So basically you find for clues, to limit the data or to limit the number of independent variables.
Right, right. So we can use this to actually limit the number of independent variables.
Yes, you can.
Yeah.
Right. So I have plotted the second one, and we see that we sort of have a similar plot over here. Not similar, actually, it's pretty much the same, right? So again, petal length less than 1.7, we get setosa. Again, we come over here, greater than 1.7, greater than 1.7, we get this to be virginica, right? So we get sort of the same result over here. Now, just to be sure, we'll again predict the values with the model which we've just built over here. So we will use the predict function, the model which we built will be the first parameter, my tree2, and we are building this model on top of the test set, and the type is response, and I will store this in my pred. Now let me again go ahead and build my confusion matrix. So first is the actual values which come from the test set. Next is the predicted values which are stored in this my pred object. I'll hit enter, right? So again, we see that we sort of get a similar result over here. Again, I'll check the accuracy, 15 plus 15 plus 16 divided by 15 plus 15 plus 16 plus 2 plus 1 plus 2, right? So we get the same accuracy. Now, with the help of this plot, we could find out that sepal length and sepal width did not provide any information to the model. And when we found out, we removed those two columns and we built the model again. So after we built the model again, we saw that this gives the same accuracy as given by including all of the independent variables, right? So this is how you basically do your trial and error. This is how you try to find out your best fit model, right? So we are done with tree. We are also done with C tree. Now it's time for the final decision tree function, which is rpart. Right. So have you also installed this rpart package?
Yeah, Varney, before going, I have two to three queries.
Yeah, sure.
Yeah, normally when you do any classification, we should not depend only on accuracy. As I mean, in the last session, as we discussed, I mean, in the logistic regression everywhere, when we are doing any classification problem, you should not only depend on particular accuracy. You should depend on this area under curve and ROC,
Yes.
and that is true positive and true negative. So, do we need to do on decision tree also or not needed?
Yes, you have. So for every classification problem, you'd have to take care of all of these factors.
Okay.
For whatever classification problem it is, you'd have to need the right trade-off between classification, specificity, sensitivity, all of these factors.
Now, suppose we got ROC some particular 0.5, 0.7. We should use that value in confusion matrix, right? While splitting the data. That means.
So could you repeat that again? So 0.7, what 0.7 is that?
Suppose ROC value, the threshold value is 0.5, 0.4 like this. We should use like in confusion matrix like this one. A table of greater than my pred greater than 0.5 or like that. We should use like that only.
For this, no, because when you use the GLM function, that gave you a probability. On the other hand, when you're using this tree function and C tree function, you are directly getting the class. You get this? So when we predicted, they directly gave us a class. They did not give us a probability, right? So this function by itself takes in a threshold value, and on the basis of that threshold value, it divides the data into classes, or it predicts the data into classes. So over here, you would not require to set a manual threshold by yourself. So in GLM, we had to do that because the logistic regression function gave us a probability.
Suppose
right? So over there, if you remember the predict, it was type is equal to prob.
Okay. Can you show us here how to use ROC for any of one of the things?
So again, so there is no point of using ROC for this, right? So we would not require the threshold for this. So, okay, so what I'll do is I will show you the predicted results of these two. So we are, okay, I'll build this model again. Let me copy this. Let me paste it over here. Wait, okay, so I'd have to load this entire thing again. Right. All right. So let me print out these values, tree dot pred. So you see that these predicted values are actually the final results which you get. You get yes, no, right? So there is no probability over here. So you don't get a probability like, there is 80% probability that this is yes, or there is 20% probability that this is no. So this function by itself takes in it takes in a threshold value and it gives you the final classified result. So all you have to do is take in this final classified result, compare it with the original result, and find out how accurate the model is. So by itself, this model will give you the optimal threshold. So this tree, C tree, and even the R part functions by themselves, they will give the optimal threshold values. So you don't have to manually set those threshold values.
Okay. There is no point of doing ROC in the here.
Yes, so again, you need to understand that we wanted the trade-off between, so ROC again gives you the threshold value for the accuracy, right? So if we cut it off at this threshold, then it says that you will get the maximum accuracy. But then again, this function by itself does that. So we don't have to manually do it. We don't have to manually set a threshold value for this probability.
Okay.
Right.
Like if we don't need to set the threshold manually, then do we need to use the AUC function? No need to use all these things in the decision tree, right?
No, not really.
Okay. And the second thing is, second question, like can we use like the same way? Because it's a multi-class classification when you're using party package. Can we use the same thing in the tree package as well, multi-class?
Yes, you can do that. So with all of these three functions, you can do that.
But for logistic regression also we can use GLM model.
No, that is not possible, I guess. So even I'm not sure. So I have never done multi-class classification with logistic regression. So I'd have to check up on that once.
No, I checked it like we have to use some other some other function that is okay. Normal
So
this thing you can use directly.
yes. So tree,
Okay.
R part, and C tree, you can directly use this for multi-class classification.
Yeah. Thank you. That's
So again, so GLM, what you need to understand is it is a binomial model and it will give you a probability. So these decision tree models, they are used for both purposes. They are used for regression as well as classification, right? So we've used, so we are done with tree, we are done with C tree. Now it's time for the R part. So with R part, we'll be doing regression, right? So this time I have the Boston dataset. So you'd have to load the mass package first. So just type in library of mass, and then you'd have to load the Boston dataset. Here, view of Boston. All right, so this is our data set over here. Now, let me actually show you what these columns mean. All right, so this Boston data frame has 506 rows and 14 columns, and these are all of the different columns which you have. So CRIM, it basically stands for per capita crime rate by town. ZN is the proportion of residential land zoned for lots over 25,000 square feet. Indus is the proportion of non-retail business acres per town. So these are different columns. You can go through this list. So our main focus would be on this MEDV column. So this MEDV is the median value of owner occupied homes in $1,000. So basically, we are trying to predict the value of this house. So this the value of this house is $24,000, is $21,000, and is like $34,000. So on the basis of the other columns, we would want to build a regression model which helps us to predict the median value of this house. So let's use the rpart function and do that. So first task again, we will have to load the rpart package. Now, again, I'm using this create data partition function, which is a part of the caret package. So this time the split column is this MEDV, and then also the ratio is 0.65. So 65% would be in training and 35% would be in test. List equals false. So we have the split tag with us. Again, what I'll do is from this Boston data, all of those values which are there in split tag, I will take them into training set, and all of those values which are not there in split tag, that is the rest of the 35% values, I will store them in the test set. So we have our training and testing sets ready. And as we've been doing, we will build the model on top of the training set. So this time the function which we are using is rpart, and right, again it's the same. So we'll put in the formula and then give in the data. So formula is MEDV tilde dot. So MEDV is our dependent variable, and all other columns are our independent. So yeah, MEDV is dependent and all other columns are independent variables. And we are building this model on top of the train set. Right. So now to plot this tree, we would require the rpart.plot package. So you guys have to load this package, and then you would have to visualize the tree which you've just built. So rpart.plot, and I will pass in this object which is my tree. Right. So this is the sort of visualization which you get from this. So over here, the first split criteria is on the basis of LSTAT. So if LSTAT is equal to or greater than 9.7, then we go on the left side. On the other hand, if LSTAT is less than 9.7, then we go onto the right side. So let's go to the right side first. So LSTAT is, let's say, less than 9.7, we go to the right side. Here we check if RM is less than 7.5. So if it's less than 7.5, again left side. So if it's greater than 7.5, we come to the right side. So this is how the split is happening. And these values which you see, these are the average values of the price of the house. So yesterday we saw that during the first example itself, when we were trying to predict the salary of the player, that gave us the average salaries of the player. So when you use a decision tree model to predict a continuous value, it will give an average value, right? So if the split goes something like this, then your average house of the price is $9,000. And if it goes something like this, the average price of the house is 15,000. And if it follows this process, then the average price of the house is $45,000, right? So this is your this is how your split works over here. Now we have built the model. Now it's time to predict the data. So this time we'll use the predict function, and we will not give the third parameter. So this time we get a continuous value, so we don't have to set the type. So this automatically gives a continuous value. So first we will give in the name of the model which you built, which is my tree, and then you'll give in the data set onto which we want to predict the values, and we want to predict the values on top of the test set. So I'll show the result in predict tree. Now I will bind the actual values and the predicted values. I'll use the cbind function. So the actual values are in the test set and the predicted values are there in this object. I will combine these two and I will store them in the final data. Now this is actually a matrix, so I will convert this into a data frame first. So as.data frame of final data, and I will store it back to final data. So view of final data. So these are the actual values and these are the predicted values which we have, right? Now what we'll do is we will go ahead and find out the error in prediction. So error in prediction is, again, we subtract these predicted values from the actual values and then we get the error in prediction. So let's do that. So it's pretty simple. All you have to do is final data $actual minus final data $predicted, and we'll store that in error. And again, we'll bind the error back to the final data. Now, let me have a glance at this view of final data. So actual values, predicted values, and this is the error in prediction. So again, if we want to find out the average error, what we have to do is there is something known as root mean square error. So let's go ahead and find out the root mean square error. So first we will take this error, we will square this up, and then we'll take the mean, and then we'll take the square root. So for the first model, we get a root mean square error of 3.93. Now I will store this in RMSE1. So again, we will take this image, and over here we see that only LSTAT, NOx, CRIM, and RM have been used, right? So out of all of the independent variables which we have only limited number of columns which have been used for the split. So we will build a model which will take in only these independent variables. So we'll not use all of the independent variables. So let's again do that. We have RM, LSTAT, CRIM, NOx. So we also have DIS over here. Let's also add that. Right. So let me add DIS. So for the second model, again, it's the same thing. Our part. So the formula is MEDV, which is the dependent variable, and the independent variables this time become RM, LSTAT, CRIM, NOx, and DIS. And we are building this model on top of the train set. So we built the model. Again, let me have a glance at this. Right. So I've hit on enter. So you did not notice any change, right? Because we've got the same result, right? I'll delete this. I'll hit enter again. So what we see is, even though we've included just these 1, 2, 3, 4, 5 independent variables, we've got the same split over here. So this again basically reiterates our belief that no other column was used for the split purpose, right? So we have built the model. Now let's go ahead and predict the values again, and let's calculate the RMSE for this model. So we'll use the predict function. So we'll take in the model as the first parameter, and then we'll predict the values on test set. We'll store it in predict tree. Again, I'll bind the actual values and the test values, and I'll store it in final data. I'll convert this to a data frame and calculate the error in prediction. Now I would have to bind this error back to the final data. So again, I will use the cbind function. So final data, I am binding the error to this. All right. Now let me have a glance at this view of final data, right? So this time when we used only these 5 independent variables, these are the actual values, these are the predicted values, and this is the error in prediction. Now again, let me go ahead and find out the root mean square error. So the root mean square error is 3.93. Now let me put in RMSE1, right? So it's the same. So for the first model and for the second model, the root mean square error is same. So this means that there is absolutely no need to include any other variable after these 5 independent variables, because they do not add anything to the model, right? So this is how we can choose our ideal independent variables. So this is how we can do regression with the help of a decision tree, right? So any doubts in these 3 functions which we've used till now?
Yeah, Varun.
Mani, we are good. I'm good, but how can we get that R file?
This I'll share this with you after the session. I'll share this with the operations team, and they'll give this R file with you guys.
Yeah, great. Thank you.
Right. And
Uh,
I was
Barney,
told that, yeah, yep,
like
go
you
ahead.
continue. I'll ask later.
Right. And I was told that I had not recorded the first half of yesterday's session, so it was basically my fault. So I believe I'd have to record the earlier part again, and then you'll have the video. So what I'll do is after today's session, I'll record the theory part again, and you'll have this uploaded by tomorrow night, right? Yesterday's theory session. Yeah,
Okay,
go
Barney.
ahead. So any other doubts?
Yeah, Barney. No, here also we should do pruning, right? In our part and C tree also.
Yes, so even here you can do pruning.
Uh, like is the same pruning method we will use or different methods are there for different packages?
No, so there is something known as train control parameters. So you will use those train control parameters for R part and C tree.
Okay.
I guess you can read up on that.
Yeah, for R part I know there is a prune mode. For C tree I was not knowing. So what was this
So
for C tree?
C tree, there are some train control parameters. So inside those train control parameters, you will, set the ideal number of maybe nodes when to split, or the ideal threshold value when to split, and that is how you do it.
Will all the pruning techniques will give the same result, right? I mean I'm not confused. I'm not sure.
So in post pruning, there is just one type, cost complexity, right? So what we saw earlier, that was cost complexity pruning. So the idea behind that is the root node, it has the highest misclassification rate. So as you keep coming down, the misclassification rate or the resubstitution error, that decreases. So you need to find those that particular level of split where the misclassification rate is minimum. So as we saw in the earlier graph, so when it reached 16 nodes, it had the least misclassification rate. But after 16, when we started splitting again, there was actually not a decrease, but there was an increase in the misclassification rate, right? So in cost complexity pruning, your idea is to have that minimum value of misclassification rate. So that minimum value where you have that minimum value of misclassification rate, that will be your ideal number of terminal nodes.
Yeah, clear. Thank you. Thank you so much.
All right.
And these were using Gini index or information gain or what
Yes,
of these methods are used?
so by default, the impurity function which these three packages use are Gini index.
How do we check that?
That again, even I'm not sure, so I'd have to read upon that. So by default, these decision tree functions which they have, so the impurity which they use is Gini. So for random forest, we'll be working with the CTG data set. So this is basically a medical data set which I took from UCI machine learning repository. So I will be sending this data set to you guys after the session. So you have to follow me through this video. So this basically consists of all of these columns, and so this is basically a data set which measures the fetal heart rate of a patient, and these are the different parameters. And this is basically the final categorical column which we are trying to predict. So this NSP basically stands for normal, suspect, or pathological. So that fetal heart rate, it's either normal or it's suspected to be pathological or it is pathological, right? So again, this will be a multi-class classification, and we'll be doing that with the help of random forest. In decision tree, we just have a single tree which we build on top of our data set. So now what we have is something called as ensemble learning. So the perfect example for this could be, let's say you want to watch a movie and you take your friend's advice. So that one particular friend hates all action movies, right? So you want to watch Avengers, and that one particular friend hates all action movies, and he has a very biased opinion towards action movies. And even though he has not watched Avengers, he'll tell you that it's a bad movie. Now, what happens in ensemble learning is you basically take opinion of multiple people. So in ensemble learning, instead of just building one decision tree, you have multiple decision trees. Or in other words, you take opinion of 10 people. And out of those 10 people, 8 people would tell you to watch Avengers because it is a good movie. Other two have their own biased opinions, and that is why they tell you it is a bad movie. So, on the whole, you will get a collective opinion that Avengers is good. So, basically, in ensemble learning, you get results from multiple decision trees. So again, the first extension um, from decision trees is bagging. And from bagging, we have something known as random forest. So what we do in bagging is we have this initial data set. So from this initial data set, we create multiple data sets, and those data sets we create by sampling with replacement. So we have this data set L with n records. What I do is I create another data set L1 which has the same number of records, and these records have been taken from L, but that is done by sampling with replacement. Similarly, I will create L2 which has n records taken from L, but these records are sampling with replacement. Similarly, I'll create another data set which is L3 which has n records taken from L, and that again is sampling with replacement. So I will create X such data sets, and I will be building one decision tree on top of each of that data set. So instead of getting just one result, I get multiple results from multiple decision trees, and I will take the aggregate result of all of the decision trees. So this is what happens in bagging. So are you able to follow me till here? The concept of bagging?
Yes, yes.
Right. So once we know what bagging is, random forest is just an extension of bagging. So in random forest, this part is the same. So first we create multiple data sets. But the part where random forest differs from bagging is the split criteria of the nodes over here. So for this split criteria, it will not get all of the independent variables. It will only get a subsection of the independent variables, and that will be a random subsection. So let's say I have 10 independent variables in my data set. Now, from those 10 independent variables, I'll be using only 3 random independent variables for the split. Similarly, for this split again, I'll be using 3 random variables. Again, for the split, there are only 3 random variables available. So, all the 10 random variables are not available for the split. Only m random variables are available. And typically, for classification trees, this m value is under root of p, and this p is the total number of independent variables. So let's say if you have 10 independent variables, then m will be under root of 10, which will be around 3 or 4, right? So this random forest is the word random in random forest is basically comes from this part over here, right? The the split of the nodes is it is dependent on random independent variables. So that is why this ensemble learning is known as random forest. So this is the only part which differs from bagging. And again, we have these X such decision trees, and we get a result from all of these decision trees. And then we take an aggregate from these decision trees, and that will be our final result. So this is the basic idea behind random forest. Right. So does that help you?
Yes, thank you.
Great. So yeah, so now that we know what random forest is, let's go ahead and work with random forest. So let me start off by having a look at the structure of this data. So I'll use the str function, and these are all of the columns which I have in this. Now my dependent column is this, which is NSP. So we see that this is of integer type, but then again, since we're doing classification, we want this to be as a categorical variable. So our first step would be to convert this integer variable into a categorical variable. And to do that, I will use the as.factor function, and I will convert this into a factor. So as dot factor of data $NSP, and I will store this back to data $NSP. Now let me have a look at the structure of this again. Structure of data, and we see that this integer type has been converted to factor. Again, let me have a glance at the levels of this NSP. So 1, 2, and 3. So this 1 denotes that the patient is normal. 2 denotes that the patient is suspected to have that fetal heart disease, and 3 denotes that the patient has that pathological heart disease. So there are 1,655 normal patients, 295 patients who are suspected to have the fetal heart disease, and there are 176 patients who actually have that pathological heart disease. All right. So now we will again go ahead and divide this data set into train and test sets and build a model on top of the train set. So now again, I'm setting the seed value to be 1, 2, 3. So whatever result I get, I can repeat that same again afterwards. So set.seed 1 to 3, and I will go ahead and use create data partition. So the split column is NSP, the split probability is 0.65. So 65% of records going to train, 35% records going to test. Now I will go ahead and take in wherever these values from split tag are there. So I will take those 65% values and store them in train set. And apart from the split tag, that is the rest of the 35% records, I will take them and store them in the test set. So here we have the training and testing sets ready. Now we will go ahead and build the random forest model on top of the training set. So for that, we would have to load the random forest package. Right, so I've loaded this package. Again, I'll set a seed value first. So the seed value is 222. And now I will build this random forest model on top of the train data. And again, this takes in a formula, and then it takes in a data, which is the training data basically. So over here, the formula is NSP tilde dot. So this means NSP is our dependent variable. So this is a dependent variable, and this dot signifies that all other columns are the independent variables. And we are building this model on top of the training set. Right, so let me just print RF over here. So this is the model which we've built. So by default, this random forest algorithm takes the number of trees to be 500 and this M value. So that M value which we saw, so this is number of variables tried at each split. This is 4, right? So by default, the number of trees is taken as 500 and that M value is taken as 4. And this is the confusion matrix for this is basically so there is something known as the out of tree error estimate. So when we went ahead and built these trees, so for these data set, not all of the rows must have come into this data set. Similarly, when we built this data set, not all of the rows must have come into this data set. So for this out of tree error estimate, what we do is the records which never entered into these X data sets, right? So we will be basically, or this algorithm will basically build this random forest model on those records which never came into these X data sets, and then it will calculate the accuracy on those records which were not part of these X data sets. So for that, the error estimate is 5.78%, or in other words, the accuracy was somewhere around 94%, right? So for those records, this is the confusion matrix, right? So all of those patients who were normal, 1060 were correctly classified as normal, 14 were incorrectly classified as suspect, and 2 were incorrectly classified as pathological. Similarly, out of those records which are left out, 51 patients who were, so 51 patients who were actually suspected to be have the heart disease, they were incorrectly classified as normal. 139 patients who were suspected to have the heart disease have been correctly classified as suspect, and 2 of those have been incorrectly classified as having pathological. Similarly, this third case, 104 who have that pathological disease have been correctly classified as having pathological disease. This 5 and 6 is the misclassification, and this is the classification error with respect to these 3 classes. So this is the random forest model which we've just built. Now let's go ahead and predict the values. So again, we'll use the predict function. First parameter is the model which you built. Next parameter is the test. So there is no third parameter over here. So this basically gives us the class labels, and we will store this in P1. And again, we will go ahead and build a confusion matrix with the help of this table function, right? So these are the actual values and these are the predicted values over here. Now, let me calculate the accuracy. So as we did in the previous examples, this left diagonal indicates all of the correctly classified values. So 567 who actually had the disease have been correctly classified as having the disease. 81 who were suspected to have the disease have been correctly classified as suspected. 51 who actually had pathological disease have been correctly classified as having that pathological disease. So the accuracy for this would be 567 plus 81 plus 51 divided by 567 plus 81 plus 51 plus 8 plus 4 plus 2 plus 5 plus 5, right? So have I missed out something? Right, so there is 20 as well, right? So 561, 81, 51, 8, 4, 2, 25, 5, right? So this gives us an accuracy of 94%. Now I will store this in, let's say, ACC1. Now what we'll do is we will try to get that optimal number of M. So M is basically the number of variables available for that split. So to get that optimal M value, we have this tune RF function. I'll set the seed value again, and I will use this tune RF function. So these are all of the parameters. So this first takes in the set of the independent variables, then this minus 22, so this is basically all of the rows except the final row. So final column. So this 22 is the final column. So I am taking all of the columns except the final column. So this is the first. Yes, so that will give us the accuracy. Left diagonal, so diagonal of variables, that's exactly actually left diagonal divided by all of the values would give you the accuracy, because left diagonal comprises of all of the values which have been correctly classified. Right, so I'll get down to this. So the first parameter is the set of independent variables. The next parameter is the set of the dependent variable, and then we give a step factor. So the step factor is basically by how much the m value should decrease or increase at each iteration. So I've set this to be 0.5, and should you make a plot when this is tuning, I set it to be true, and then we have this n tree try. So the optimal m value, I want it when the number of trees are 300, right? So I'm taking the number of trees in this random forest to be 300, and I want the optimal m value for this set of number of trees. This trace basically gives us a trace when this model is building, and improve is like by how much factor does it have to improve after each set of iteration it goes through. So I have assigned that to be 0.05. So this basically gives us a graph which is something like this. So first, let's have a glance at this. So now the number of trees which we have is 300. And when the number of trees is 300, so this first tries out with the m value. So initially, the number of variables, independent variables available for it were 4. And when the number of independent variables available were 4, the OOB error was 6.15. And then it tried with 8. So when it tried with 8, the OOB error, it came down to 5.71%. After that, it tried with 16. So when it tried with 16, it again increased. So what we see is when the number of trees is 300, the optimal m value is 8, right? So that is what we see over here. So 2, 4, 8. So from 2 to 4 to 8, the error is decreasing. But then again, after 8, you provided more number of random independent variables, then the error will actually increase. It will not decrease. So we have found out the optimal number of optimal m value for this. Now we will go ahead and use that m value and build our random forest model again. So I will set the seed again, and I will use the random forest function. So again, the dependent variable is NSP, and the rest of the variables are the independent variables. I am building this on top of the train set. Number of trees are 300, and the m value is 8. Now let me print out RF, and this is what we get over here. So this time the out of box error estimate is 5.86. Now let me go ahead and predict the values. I'll use the predict function. Again, it takes in two parameters. First, right, so this train, so this is basically the, okay, I'll do this tune RF, I'll hit a tab, right? So this train minus 22 is the metrics or data frame of predictor variables. This train 22, this is the response factor. So first we given the list of the predictor variables in this. So except the last column, rest of them are the predictor variables, or in other words, they are the independent variables. After that, we need to give in the response factor or the dependent variable. So the response factor is this 22nd column. And then, so these are the different attributes which we're going to, out of these, we have used the plot. So this plot basically gives us whether to plot the OOB error as a function of m try, and then we use the n tree try, which gives us, which over here we are basically setting the number of trees to use. Trace, this gives us whether to print the progress of the search, and then we have improve, the relative improvement in OOB error must be this much for the search to continue, right? So whatever parameters we are giving, then, yep, go ahead.
Barney, just a moment. I'm not understanding the train and this thing. Train of minus 22 and 22. I didn't understand
Okay.
that part clearly still.
Okay. So I'll just print it out then. Okay, so did you follow where we were dividing the entire data set into train test, into train set and test set, right? You're able to follow that? We had this
Yeah, yeah,
original data
yeah,
set
yeah,
and we had
yeah,
divided
yeah.
that into train and test. Now, after that, we built a model. After that, we are trying to find the perfect M value. So to find that perfect M value, this tune RF function takes in certain parameters. So the first parameter is the data frame consisting of all of the predictor variables. Now I will show you the train data frame. So this is the train data frame which consists of all of these columns. Now from this entire data frame, I will select all the columns except the 22nd column, and I will name this as I don't know, minus 22. So view of minus 22, right? So over here, if you see this train data set, this has the NSP column, but in this minus 22, we don't have the NSP column, right? It ends at tendency, right? So this basically train comma minus 22 takes in all the columns except the final column. So this you must have learned in the initial classes where you are trying to where you are learning how
Yeah,
to index the
this
rows in
no,
columns. Yeah,
yeah,
go
this is
ahead,
okay.
Sai.
Again, you used train of 22. What is that? Again, you are
Right.
using the
So
same command, train of 22. What is that?
right. So this is only the final column. Right now, I will maybe store this as plus 22 view of plus 22. So this has just one column. So we had this entire data frame. Now the first parameter is just the predictor columns, which are all the columns except the NSP column. Next parameter is the dependent column. So when we want the dependent column, we just give in the column number, right? So this comprises of only the dependent column. So from this train data frame,
Yeah,
if
okay.
we want, yeah, so you understood that?
Yeah, I understood. Actually, there were, I mean, no proper internet connection with my end, so I missed that particular thing. Thank you so
Okay,
much.
right. Yeah, I'll also close this. Right. So these are all of the parameters which we have in this, and we found out that the optimal number of M was 8. And so let me actually print this out again. Right. So the optimal number is 8. I will also print this RF value. I will go ahead and predict the values now. So we know the optimal M value, and with respect to that optimal M value, I am building a forest and I am predicting the values on the test set, and I am storing that in the P2 object. Now, after that, I will go ahead and build the confusion matrix. So this again takes in two parameters. First is the actual values, next is the predicted values which are stored in P2. So this is the confusion matrix which we get. So okay, so how many how many of you guys have still doubt with this confusion matrix, right? Are you able to follow how am I calculating the error with this confusion matrix? Because I had a question regarding this, right? Others, everyone is clear with confusion matrix, right? How do you understand this? Like, how do you interpret this confusion matrix, and how do you get the accuracy from this? Okay, great. So I'll just go ahead and calculate the accuracy then. 566 plus 83 plus 52 divided by 566 plus 83 plus 52 plus 8 plus 5 plus 2 plus 5 plus 4. So have I missed out on anything? There's 18 as well, right? So 556, 83, 52, 8, 5, 2, 18, 5, and 4. All right. So this time we get an accuracy of 94%. ACC 1, it was 94. It was 94.07. So after we set the number of trees to be 300 and the mtry value to be 8, we get an accuracy of 94%, right? So basically with this, we get to know that initially the number of trees were 500 and the mtry value was 4. But then with the help of tune RF, we did a bit of tuning, and we wanted to get the optimal value for when the number of trees was 300, and we found out that the optimal value of m should be 8 for that. And when we set the number of trees to be 300 and the m value to be 8, we got an accuracy of 94.34, which is just a slight improvement over the previous model. So this is how you can tune the parameters. So again, this random forest just consists of two variable attributes, which is n-tree and m-try, right? So you can play around with these two to get
Sorry,
the
what
ideal
is,
accuracy.
can you elaborate again on mtry? I somehow missed that.
So do you want me to cover this tune RF again, or only
No,
the
tune
m-try?
RF is fine. mtry, what is the significance of mtry?
M-try is just this m value. So m-try is the m value, the number of variables or the number of random variables which we give to the split. That is your m-try or your m. So in this run, so that is this m-try.
But still, we are
N-tree is
feeding in, at this point in time, we are feeding in all the variables and saying that in one decision tree, maximum you could use is 8 variables to split.
no. So for this random forest, so over here, let me check the number of columns. So
You have
call,
23, right? 22 or 23, yeah.
so we have 22. So out of those 22, for each split, we are giving only 8 of those columns. So that is what we are doing over here.
Any 8.
Yes, any 8, any random 8. Right, so that is what m does over here, right? So for each split, there is n random subsection of the independent variables. So for this split, there'll be 8 independent variables. For this split, there'll be 8 random independent variables. For this split, there'll be 8 random independent variables.
And where do we see the weightage of each variable that is influencing the model?
Right, so we'll go to that. So there is something known as the importance function or the variable importance function, and we'll also cover that.
Okay.
So
right.
One more thing, how we are optimizing entry? Randomly we took 300, is it right?
Yes. So again, what you can do is you can set random values. So this again, you'd have to play by yourself. So you can set this as 400 and get the optimal value for 400. This you can set to be 1000 and get the optimal value for 1000. So these hyperparameters, you'd have to tune them yourself. So this is again trial and error.
Okay.
And is there anything on random forest? Is there anything to do with depth of the tree?
Depth of the tree, you mean to prune it? Is it?
Yeah, I mean, to what depth we can take it, otherwise it will be like an overfitting. I mean, is there something like that?
There would be, but then again, I'm not sure. So you'd have to read upon that. But then again, there should be something where we could, prune the trees first and then use only those pruned trees in the random forest. So you guys have to read upon that. Right.
Okay.
So we're done with the prediction. Now after this, we want to see the number of nodes for the different trees which we have. So we'll just build a histogram, and there is this tree size function which is a part of the random forest package, and will pass in the model which you built. And I am giving this histogram a name of number of nodes for the trees, and the color for the histogram would be green. So right, we see that there are around 80 decision trees which have around 80 nodes. So again, so there are, so this frequency is of the number of decision trees you have in the random forest, and this is the tree size or number of nodes. So you can say that there are around 10 or maybe just 5 random forest, 5 decision trees which have around 100 nodes. So this tells you there are around 20 decision trees which have around 60 nodes. You have around 50 decision trees which have around 70 nodes. So this is what this histogram tells you. And then, yeah, as Sanjeev was asking, we have something known as variable importance. So this var imp plot gives you the relative importance of all of these variables. So this takes all of these parameters. So var imp plot, and I will pass in the model which I built, sort. So this will basically sort this with respect to the importance of the variables. So the number of the top number of variables which I want to see. So this will give me the top 10 variables which are important, and I've given the title which is top 10 variable importance. So this, what you see is mean decrease Gini. So again, as we saw in yesterday's class, so the root node has some Gini index value, and then the aggregate leaf nodes have some Gini index value, and that tree which has the maximum decrease in this Gini index value, or in other words, that tree which has the maximum gain in information gain, that would be our that is basically our ideal split. So this tells us that ASTV would be our ideal split. So this we split it with respect to ASTV, then we'll get the ideal split. After that, the next most important is MSTV, then we have ALTV, right? So we see that these 4 are the most important. After that, there is a significant gap between mean and DP. So what we can conclude is the major variables from this are ASTV, MSTV, ALTV, and mean. Right. So Sanjeev, this is how we can find out the relative importance of the variables. So if I want output on the R screen, I'll just use the importance function. Yeah.
Yeah, you just mentioned that this will tell me the importance of the variable in the model, or is it really telling me that what is the contribution of this variable to the variability or the predictability of my dependent variable?
So when you say importance, it basically means how much does the independent variable affect the dependent variable. So this ASTV has the most amount of impact on the dependent variable, followed by MSTV, followed by ALTV.
Yeah, but is it a relative importance? Because the thing is that probably all these variables would be having just a import, or would be impacting the dependent variable to an extent of 10%. Within that 10%, then this is the importance of each of the variable. Is this how it is telling me, or is it saying that okay, whatever is happening to the dependent variable, ASTV is accounting for almost 90% of that predictability? What does it tell?
So okay, so you can take it this way. So ASTV has the maximum effect on the dependent variable. So this is what it tells you, right? So again, so out of all, okay. So let's say I want to build a model using the variables. So I want to know if, okay, so let's say if I want to build a simple model with just one independent variable, then in that case, I would want that independent variable which affect the most. So this would be that independent variable ASTV. So if I want to build a model which has 2 independent variables which would affect the dependent variable the maximum, So in that case, ASTV and MSTV would be those independent variables. If I want to use 3, then these 3 would be that. So again, from this plot, what we are doing is we are again building a model where we'll be using only these 4 independent variables, because these 4 independent variables affect the dependent variable the maximum. Right, so they basically cover the maximum variance of the dependent variable. So are you still confused?
Just show the scores, can you run the importance function? Possibly that will help.
No, so this again basically gives you the mean decrease Gini. So what you have over here. So this again tells you that MSTV, which is over here, and then we have ASTV, right? So ASTV, this is the maximum. So this tells you ASTV has the maximum effect on the dependent variable, followed by MSTV, followed by ALTV. Right, so are you guys confused, or is this clear, the importance?
Yeah, got it.
Right, so now once we know the importance or the order of importance of the independent variables, we'll go ahead and build another random forest model where we are using only these 4 independent variables, which are MSTV, ASTV, ALTV, and mean. And in the previous model, we had set the number of trees to be 300. So that is what we'll be doing over here. So we are building a model and we are storing that in RF, and we will predict the values. Right. So again, RF is the model which you built, and we are predicting the values on top of the test set. Now, after this, we will go ahead and build the confusion matrix and find out the accuracy. So 564 plus 73 plus 53 divided by 4 plus 73 plus 53 plus 2 plus 3 plus 7 plus 8 plus 1 plus 29 plus 6.
You did it wrong. You did it wrong. 2, 3 is not there.
2, 3. Oh yeah, sorry for that. So 564, 73, 53, 8, 7, 1, 29, 6, and 2. Right. So we get an accuracy of 92%. So let me just check ACC1, which was 94. ACC2 was also 94. So we see that these 4 independent variables, these are, so when we use only these 4, they themselves give us an accuracy of 92%. So the other variables, they just add up to 2%, right? So these are the, so when we use just these 4 independent variables, they are the variables which, which significantly impact the dependent variable over here. So this is again another way to, tune your model, right? So
just a moment.
Yep.
What was could you show up the NSP column? Is it categorical value or continuous value? The NSP column.
So initially this was an integer. Okay. I used the as.factor function and converted that into a factor. So class of data dollar NSP. Right. So yeah, so this is all about random forest.
Yeah. Normally when we use GLM function, we used to get probabilities. When we use GLM function, we used to get probabilities. When we use tree modation to any model, we used to get the classic that yes or no that output. For this, what we are getting after building the model?
So even for this, we are getting the final class result. So, okay, I'll just print out T3 over here. So, right, this is what you see. So for 11th record, the class is 1. So for 21st record, class is 3. So for record number 175, class is 1. For record number 417, class is 2. So you get the final class for random forest as well. Right, so if you have any doubts, you just print out this value. So I'm just storing this in P3 so that I can use it later. So normally, if you just print this out, you'll get the list of predictions. Right.
I have seen in one session, I know in YouTube somewhere, they use the ROC and AUC on random forest model, but here then no need to use it. As per before you said, when it's giving classification, that no need to use. But I have seen when one video like they use the ROC for this model, random forest model, using PROC package.
Okay. So maybe in that case, the prediction type would have been probability. So let me just check. So normally what I do is I just get the classes.
Yeah, it's correct.
Yeah. So let me write. So in this case, when I set the type to be probability, I get the probabilities. So this is where I will, maybe set a threshold. But then again, what the algorithm does is it automatically takes a threshold value and it classifies it itself, right? So if I want to manually set a threshold, then I can look at the, Yep. So right, guys. So this is it for today's session.
One more thing.
Yeah, go ahead.
Yeah, one more thing I was asking. I forgot now. I'll just 2 minutes. I'll remind again.
Sure. So others, any questions?
What is the use of? Yeah, got it. We are using type equal to response, type equal to class. What is the meaning of type equal to response and class? What's the difference? Both. I was confused. There's a small line between that. I was not sure exactly.
Yes. So that is the
then
nomenclature.
We are using for C3.
So that is the nomenclature difference with respect to the different functions you have. So this, where do we, yeah. So when it comes to the tree package, the nomenclature which you'll use when you want to do the prediction, that will be type is equal to class. So again, when it comes to the C tree class, so this time, basically, if you put this as class, it will not work. So it's just the nomenclature difference. So I will plot this out over here. And if I set this to be class, right? So this is what you get, right? So basically, it's just that this function takes in the type as a response. So it does not recognize class. So it's just that the nomenclature difference of whoever has written that package, that person has specified the type, the predict type over here to be response instead of class. So similarly over here, for our part, yep. So over here we did regression, so we don't need to do that. So again, for random forest, so whoever had created this package for he set the nomenclature like this. So if you want probabilities, then he set the nomenclature to be PROB. So it's just a nomenclature difference. So if you again, so if you want any help, all you have to do is search for it. So random forest, and you will get all the help you need with respect to this package over here. You'll have all of these things: predict, plot, tune RF. So whatever parameter you want to use or whatever function you want to use from this package, you can get it from the help function.
Got it. Last and final question, Barney. We use Logistic, random forest, decision tree, all for classification. I mean, for these
decision and random forest are used for both classification and regression.
Yeah. Suppose now, how do we decide when to go for logistic, when to go for random, when to go for decision tree?
So random forest is always better than decision tree and logistic regression. That is for sure, because ensemble learning gives you a collective result. So when you compare decision tree and random forest, you should always go for random forest. So, ensemble learning is, so, if you build a single decision tree, it'll give you one result. But if you take that decision tree and you create 100 replicas of it, then you'll get a collective result of those 100 replicas. So random forest or whenever or any sort of ensemble learning it is, that is, ensemble learning is always better than a single model which you use.
Okay. And when we go for these things, suppose now these two are clear. Like on what, when we, how do we decide we should use for particular data set we go for logistic, particular data set we go for the random forest? How do we give any idea you can give us?
So logistic regression, what I'm thinking is it's mostly for two-way classification. So I'm really not sure if you can use logistic regression for multi-way classification. So I'd have to read up on that. So again, so I'm just assuming over here that random forest and decision tree come in better when we have multi-way classification, and logistic regression we use when we have these two classes. But then again, don't take my word for it. Even I'm not sure of it.
We will use for multi-class for logistic regression. For that, I mean, for information I'm giving just for you. Like for that, we use multi-norm function. For that, we need to download n net package.
Okay, so that's neural networks. Okay.
That there we use for GLM model. But I was confused. Suppose if it's a two-type binomial classification, when to go for these two, we would give it will be better for us to on data set to try out.
Hello.
Yeah. Can you hear me?
Yeah.
So Sai, there's no thumb rule to this. Okay, whenever you start doing the modeling, right, you have to see the predictions and the accuracy. Okay, whether you get a better accuracy with logistic model or whether you get a better with decision or random. I mean, decision typically is not being used. We always go for random in case we have to go towards this direction. But you will have to create the models, tune those models, and compare the results. That is how you do it. It is always trial and error. There's no thumb rule as such. That this would work better in this case, or that would work better in that case.
Okay. Thanks, Sanjeev. Thanks a lot.
Barney, one point, right? I mean, when we were doing the assignments earlier, there were a couple of topics that we listed down. Will you be covering those?
Yes, so I spoke with the team. So what they told me is they are not part of the course curriculum. So imputation, so you guys had listed down imputation, there was multicollinearity. So they are not part of the course curriculum. So I can only cover those topics which are part of the course curriculum. So that is the case over here.
Okay. What are the topics which are remaining now?
So now we will head on to unsupervised learning. So in unsupervised learning, we have recommendation engine, we have clustering topics. So we'll go to these two. So that is what we'll be covering in the next session. So after that, so I'd have to look up at the course curriculum first. So in the next session, it'll be totally unsupervised learning. So in unsupervised learning, first would be the clustering techniques. After that, we'll see how can we build a recommendation engine. So in recommendation, again, you have something known as user-based collaborative filtering and item-based collaborative filtering. So we'll be looking at both of them.
Barney, do we covering PCA? Like in unsupervised learning, we have PC, principal component analysis. We for dimension reduction techniques. Are you teaching that to us?
Yeah. So again, so for next session, even I'd have to look up at the course curriculum. So two things are for sure. So there is k-means clustering, which I'll be definitely teaching, and there is recommendation engine, which I'll be definitely teaching. So the other topics, I'd have to look up the course curriculum first.
As per the
so
course
these two are
curriculum,
definitely there.
Yeah, as per the course curriculum, like we need to cover ARIMA model, like time series and sentiment analysis, and for this recommendation engine and unsupervised. These four things I think we need to cover.
Yeah. So recommendation engine and k-means clustering, I'll be doing that in next class. So time series and sentiment analysis, that'll be most probably the weekend after weekend.
Yeah, okay.
So, yeah, any other questions with respect to what we've covered today?
That will be all. Barney, if you can, if you don't mind, can you send the additional topics that we listed on the other day?
Again, so I've been told that I need to
That's
follow the
fine.
course.
What you
Yeah.
haven't told is fine. I just want to have that list actually. If you don't mind, you can paste it in the chat window anywhere, that should be fine.
Okay, so what I'll do is I'll send that list to the operations team. I'll send that to the pack.
Bernie, please send the data set for this one, random forest.
Yes, so today I'll be sending these two files and the data set.
Yeah, that will be good.
And again, there'll be a feedback form which you'll have to fill up for today's session. Walid, is this regarding the feedback form? So everyone, you'd have to fill up the feedback form.
Where we get the feedback from?
So after I end the session, you'll automatically get the feedback form.
Okay. Bernie, the topics are like last time we discussed. Few topics like one is multicollinearity, and the second one is like treating missing values and outliers, and the next one is like this one weight of evidence. These topics.
Right. So again, as I said, I cannot deviate from the course curriculum. So if these topics are not listed in the course curriculum, then I won't be able to teach those topics to you.
Yeah, that is okay. Like at least if you get like suppose now today half an hour is finished. Like at least you can give overall idea. Like take any data set and give like how to treat missing values, outliers. At least that will be just half an hour. That will be good for us.
Again, so I sorry for repeating the same thing, but that again is not in my hands. So yeah.
I mean, if there is time, you can explain to us. Like I'm the time. It will be better for us.
Yes.
Because if you miss that particular thing, like even though we know the models, the after these things are the before step we need to go for the modeling. That is important. I feel the scaling and all. When we don't know those things, how do we implement those? It will be a bit difficult for us to implement the model.
Right. So
Just half an hour, 45 minutes.
Yeah. So again, so the only thing that I can do is ask the operations team if they can, schedule an extra session regarding these extra topics. So maybe like if you guys are free, I can take one session in the morning and one session in the night. So like, so this session is from 8 to 10. So like I can take a session in the morning as well. So from 7 to 9. So if the operations team allows that, then that is something I can do.
I am okay for that, and we need to ask for all the group members for morning session.
Yep, and I believe this can happen only once we cover all of the modules first, right? So first, I'd have to finish off the whatever modules we have. After that, the extra topics which have been listed, I'd have to cover those extra topics.
Yeah, that's fine, Gordon. That is okay. At least at last also it's fine for us.
So okay then, I'm ending the session for today, and right. So today we'll start off with clustering, which is an unsupervised learning algorithm. And we'll be understanding the k-means algorithm today. And even today's session would be mathematical. So we'll be understanding the math behind the k-means clustering algorithm. So this, what you see over here is our iris data set, which comprise of these columns. So we had to work with this data set in our previous session. So we have sepal length, length, petal width, and the final species column. Now, what we are basically doing is we are trying to build a clustering algorithm on top of this data and understand what happens behind that clustering algorithm. Or basically, we are trying to understand the math behind that clustering algorithm, right? So, okay, so let's start off. So this is our data set over here. Now, our first task would be to get the centered values. So these centered values are basically the values when you subtract each individual value with its mean value. Now let me just scroll down. So over here you see the mean values of each of the columns. So for sepal length it's 5.8. For the rest of the columns, these are the values. So what I'm doing is I am basically taking this value over here in the first record 5.1 and I will subtract that with the mean and I get this centered value. Similarly, I take 4.9 and subtract with the mean value and I get this centered value over here. Right? Again, I'll take this 4.6, I'll subtract with the mean value, get this value. Similarly, for sepal width, again, it's 3.5 over here. So I'll subtract the 3.5 with 3.05 and I will get this centered value over here, right? So this is how we can, this is how we get what is something known as a centered value. So it's basically, we have the original values and we are subtracting those original values with the mean value, and the resultant value which we get over here, that is known as the centered value. So we basically get these centered values for all of these 4 numerical columns for all of the records. Now we are not basically interested in the direction of these numerical values. We want the magnitude. So wherever we have the minus symbol, so basically we do not want these minus symbols. So that is why we get something known as the centered square. So centered square is basically the square of this value over here. So when you square this up, that is what you get. So when you square this minus 0.74, you get 0.55. Similarly, you take this value and square this up, you'll get this value over here. Similarly, you'll take this value, square this up, you'll get this centered square over here. So is everyone following me till here? What we're doing? We have these original values. We will subtract those original values with the mean, and then we get the centered values. Now we'll take these centered values and then we'll square them up, and the resultant is centered square. A quick yes or no? Are you guys following me till here? Yes. Okay, great. So this, what you get is basically the deviation in the original values, or the deviation from the mean of the original values. Now let me come down. So what I'll do is I will add up the total deviation in this sepal length column and I get a value of 102. Similarly, I will calculate the total deviation in the sepal width column. I get this value. Similarly, I will calculate the total deviation in petal length. I'll get this. I'll calculate the total deviation in this column and I'll get this. So basically, this is the sum function. If you have a look at the formula, I am basically summing this up. So from row number 2 to row number 51, I will sum up this entire column and I get the total deviation or the total variance for this column. Similarly, I'll sum up this, I'll get the deviation for this column, I'll sum this up, I'll get the deviation for this column, and I'll sum this up and I'll get the deviation of this column. Now, these are the variations with respect to each individual column. Now, if we add all of these individual deviations, then we will get the total deviation or the total variance present in the data set, and that is what you have over here. So this 681, this is also known as total sum of squares, and this total sum of squares basically denotes the total sum of the deviation present in the data set. So now This again is with respect to all of the columns. Now, if we want this variance with respect to each individual record, what we have to do is divide this value with 150, because there are 150 records in total, and these are the values for 150 records. So this is the final value. Now, if I divide this final value with 150, I will get the variance present in each value of the sepal length column, and that will be 0.68. Similarly, I'll take this value and divide it with 150 and I get a value of 0.188. Similarly, I'll take this third column, divide it with 150, I'll get 3.09. I'll take the fourth column, divide it with 150, and I'll get this column over here. Again, if I add up this entire thing, then I will get the variance present in one entire record, right? So if someone asks you how can you calculate the variance present in one single record, then this would be the way to calculate it. So everyone following me? A quick yes or no?
Yes.
Why would you say variance as a square of the values? I mean, why don't you do the square root and then say that that is the variance?
So again, so we would not want the negative value over here. We are only
No, I
interested.
understand that part. My point, my question is different. I understand this part that you square. I mean, do that square. That's a positive value, but now it's a square value what you're having. So unless you do
Yes.
the square root, you will not get the variance, right? You're getting a variance in the terms of squares.
Yes. So, Sanjeev, you'd have to wait a bit. So all of this, you'd have to wait for 10 more minutes and all of this will add up. So these values which you have, this is known as total sum of squares. And this is exactly what we'll be using in the k-means algorithm. So we have something known as total sum of squares, we have something known as between sum of squares, and we have something known as within sum of squares. So these are the three important components when it comes to k-means algorithm. So this was basically an idea to tell you, how to calculate the total sum of squares, right? So I mean, just understand that total sum of squares, as you can consider this to be the maybe the total not exactly error. Again, it is not exactly variance. You can consider this to be a sort of deviation, the total sum of the deviation present in this data set. Right? So is that good for now?
Yeah, let us proceed.
Yeah. So for now, just consider that this 680 which you have, this is the total deviation which you have in this data set. Now, let me open this summary tab over here. So this is the same thing. So we have these let me slide this up, right? So we have these 4 columns and this is our entire data set. Now this, what you see over here, this is basically sum of squares. So what I'm doing is, let me go over here. When you add these values up, the centered square values, right? So when you add these 4 values up, you will get this total sum of squares with respect to one record. Similarly, when you add these 4 up, again, so this would be these values. When you add these 4 up, you will get the total sum of squares for the second. Similarly, I've done the same thing for all the 150 records. And when you add all of them up, this basically becomes 681, right? So when you add this up, you will get 681 over here. So any doubts still here? What is this SS? So this is basically the sum of errors with respect to each record. And when you add all of these, you will get the total sum of squares, which is 681. Now, we have these cluster IDs, which we have got after we implemented the k-means algorithm. Again, just have a look at these cluster IDs. We'll understand how these cluster IDs were assigned later on, right? So we've implemented the k-means algorithm, and the k-means algorithm, it took the first row and placed that first row in cluster 1. It took the second row and placed the second row in cluster 4. Similarly, let me go down. It took the 54th row maybe and it placed it in cluster number 3, right? So basically it has taken each individual record. Now, when it comes to k-means algorithm, these individual records are basically data points. So there are 150 data points in total, and it has taken each data point and placed each of that single data point in one cluster. And as we see over here, we have 4 clusters, right? So 1, 2, 3, and 4. So basically there are 150 data points, and we have clustered those 150 data points into 4 clusters. Now, after doing this, what I'm doing is I have divided this data set with respect to the clusters they were formed. So whatever records were present in cluster 1, I've segregated them and put them over here. Similarly, whatever records were placed into cluster 2, I've segregated them. Again, these are all the records present in cluster 3, and then we have all the records present in cluster 4. Now, for each of these separate clusters, I have calculated the width and sum of squares. So this width and sum of squares, again, we're doing the same thing. So this will be 5.1. We'll get the center value, which will be 5.1 minus the mean of this, and then we'll take the square. So when we do that, we will get this width in SS. Again, we'll take this 5, we'll subtract it with respect to the mean, and then we'll take the square, and this is what we get over here. And we do that for all of the 150 records, and the total within SS which we get for first cluster is 4.63. So now this within SS, you can consider this to be the total deviation present in cluster 1, right? So the total deviation or the sum of squares present in the first cluster or within the first cluster is 4. Again, we'll do the same thing for cluster number 2. So in cluster number 2, again, I've taken these values. So this value minus the mean of it, and then we'll square it. Similarly, we'll add all of these, and then we'll get this within SS. So similarly, what I'll do is I'll calculate within SS for all of the 150 records, and this is the total deviation or the within sum of squares present in cluster 2. Again, we've done the same thing for cluster 3 and cluster 4. So we've calculated within SS separately for each record, and then we've calculated the within SS for all of the 150 rows. And then we have the cluster number 4. Again, we've calculated within SS for each record, and then we have summed it up and got the total within SS for cluster number 4. So everyone following? Within SS? You understand?
When we are taking a mean within a cluster and then doing a subtraction.
Yes, that is what we are doing. So this mean value of this column over here. So if we take this cluster 3, then we will be subtracting this 7 with the mean of this column and then square it. After that, it will be plus of 3.2 minus of mean of this column and square of it, plus 4.7 minus mean of this column, square of it, plus 1.4 minus mean of this column, square of it. So that is how we get this value. Everyone else?
Bernie, how did we give that cluster number there? Like randomly
Again,
we gave
so
or what?
No, so these cluster numbers we've got after we've implemented the k-means algorithm. So for now, just understand that these cluster numbers have been generated by the k-means algorithm. So after that, when we're doing the demo, with R, we'll understand how it's happening.
Okay, how theoretical algorithm? How theoretical it works? Like to give the cluster ID.
Could you repeat that, please?
I mean, algorithm works based on some logic, right? That it will give separate based on some logic, right? These clusters. How do that? What will the theory behind that? What logic? If you want to do it manually, how to separate that?
Yes, so we will also cover that again. So that again, you'd have to wait for 10 more minutes. So first, this math is important. So first, we'll complete this math, and then we'll head to the theory, and then we'll head to the practical.
Okay,
Right. So just a bit of patience.
I don't know whether you'll address it later on, but just I have not even understood what is this k-means algorithm. So while I'm getting the calculations, what you're doing, but I'm not just what is the significance and the relevance of k-means algorithm. So you're going to take it later on? How is it?
No, I'll do it right now. Okay. So I'll start from the beginning then. So k-means algorithm is a clustering algorithm, and a clustering algorithm is an unsupervised algorithm. So the difference between unsupervised and supervised is there are no labels when it comes to unsupervised learning. Right? So this is the basic difference between supervised and unsupervised. And in unsupervised, you try to understand the structure of the data without any labels. So again, so this data set which you take, so you will not be, so what we do in supervised learning is we divide the data into training and testing set. So all of that will not be doing when it comes to k-means clustering. So we will just give this data to the k-means clustering algorithm, and the k-means clustering algorithm will divide this data set into clusters. Now, these clusters, the idea behind clustering is there needs to be high intra-cluster similarity and there needs to be extremely high intra-cluster similarity, and there needs to be high inter-cluster dissimilarity. Right? So these terms you need to understand: high intra-cluster similarity and high inter-cluster dissimilarity. So when I say high intra-cluster similarity, then what I basically mean is the data points which are present in cluster 1 are extremely similar to each other. And what I mean by inter-cluster dissimilarity is the the similarity between cluster 1 and cluster 2 should be there needs to be no similarity between cluster 1 and cluster 2, or in other words, there needs to be quite an amount of dissimilarity between cluster 1 and cluster 2. So is it still confusing? So in simple terms, a clustering algorithm takes in the data and divides the data into multiple clusters on the basis of the features of the data points. And the idea behind these clusters is to increase the inter-cluster similarity and decrease the inter-cluster similarity, right? So this is the intra-cluster similarity. So all of these data points which are present in cluster 1 needs to be similar. So instead of saying intra, I'll say within. So all the data points within this cluster 1 needs to be similar. So this is within cluster similarity. And then we have, so instead of saying inter, I'll say between. So we have between cluster similarity. So this between cluster similarity, it shouldn't exist. So these needs to be quite dissimilar over here. Cluster 1 and cluster 2 needs to be dissimilar, but data points in cluster 1 should be similar, data points in cluster 2 should be similar, and all the data points in cluster 3 should be similar. So making sense, or do you guys still have doubts?
No, this
so
is
again,
fine.
we'll be covering the entire thing. It says that the math will connect to everything. Any doubts, Tilio? What is a clustering algorithm? What are we doing over here? What is the aim behind the clustering algorithm?
I am fine with it. Yeah.
Others, a quick yes or no? Okay, so a quick yes or no till what we've covered. So are you able to follow how we are calculating this within sum of squares? Everyone, a quick confirmation, please. Okay, right. So we have got the within sum of squares with respect to each of the clusters now. So right, so this is the within sum of squares for cluster 1, This is the within sum of squares for cluster 2. This is for cluster 3, and then we have the within sum of squares for cluster 4. Now, what I'll do is, right, so in the previous section, we had, right, so again, I'll be covering the process flow behind k-means. It says that the math is important to understand first. So in this tab over here, we had calculated the total sum of squares, and this total sum of squares came to be 689. And in this tab, we have calculated the within sum of squares for each of the clusters. So within sum of squares for cluster 1, cluster 2, cluster 3, and cluster 4. Now, when you add up all of these within sum of squares for each of these clusters, you will get this value. So this is what is known as total within sum of square. Now, if you look at these two values, so this was the case before applying the k-means algorithm, and this is the case after applying the k-means algorithm. So before we applied the algorithm, the value of total sum of squares of the deviation in the data set was 681, and after we applied the k-means algorithm, it came down to 71, right? So initially it was 681. After that, we applied the k-means algorithm, and this total sum of squares, it came down to 71. Now my question is, where is the rest of the error? Right, so this is the initial sum of squares. This is after we applied the k-means algorithm. So with the math, you can understand that the deviation in the total sum of squares has reduced. Everyone agrees with this? So my question to you guys is, where is the rest of the error? Where has it gone?
How can we get 7145?
So this was the within SS for cluster 1. This is the within SS for cluster 2, within SS for cluster 3, within SS for cluster 4. If you add all of these four values, you'll get 71.45.
Okay. Thank you.
Right. So anyone? So now, are you guys able to understand what is happening over here? Any clue how the k-means works? So this was the initial scenario. We applied k-means, and k-means gave us 4 clusters. And after and when we looked at this total within SS, we saw that the deviation reduced. Okay. So what we are doing is, as I've already told you, there is intra-cluster similarity and inter-cluster dissimilarity. So this value needs to be as low as possible. So this is total within sum of squares. Now, if this value is as low as possible, this means the elements within the cluster are as similar as possible, right? After that, we have this between SS. So this between SS is the sum of squares between the clusters. So this is the within cluster sum of squares. This is the between cluster sum of squares. So within the clusters, all of the points reside, and when you sum up the sum of squares with respect to all of these clusters, it comes up to 71. And the 609 is the between sum of squares between the 4 clusters, right? So what you can understand is there is very high amount of similarity between inside the cluster 1, inside cluster 2, inside cluster 3, and inside cluster 4. But when you try and if you want to see the similarity between the clusters, so you want to see if there is similarity between cluster 1 and cluster 2, or cluster 1 and cluster 4, or cluster 3 and cluster 1, right? Then the between SS is quite high. And this is the aim of the k-means algorithm or any other clustering algorithm. So the clustering algorithm takes in a data set, it divides the data set into clusters. Now the within cluster similarity should be high, and the between cluster dissimilarity should be high. So everyone following? what is total sum of squares, within sum of squares, total within SS and between SS? Everyone following till here? So this is the basic math behind k-means. A quick yes or no? Yes? Okay. Right. So keep these things in mind. The last part again, okay, the summary tab, I'll do it again. So in the variability section, we had calculated the total sum of squares for the entire data set, and it came up to 681. Now, after we did that, we went ahead and applied the k-means algorithm. So the k-means algorithm divided this data set into 4 clusters, and what we did is we calculated the within sum of squares for each of these clusters. So we have the within sum of squares for cluster 1, cluster 2, cluster 3 and cluster 4. So this is the within SS for cluster 1, within SS for cluster 2, within SS for cluster 3 and within SS for cluster 4. Now, if you add these 4 up, you will get the total within sum of squares. So this 681, what you see is a total sum of squares before you applied the k-means algorithm. And after you applied the k-means algorithm, this came down to 71. So from 681, it came down to 71. Now, you guys need to understand that all of the 150 data points reside only in this 4 clusters. So again, when it comes to these 4 clusters, the similarity is very high. That is the reason why this deviation, it came down from 681 to 71. So the rest, so when you add up 609 plus 71, you get 681. This rest 609 is what you call as between sum of squares. So this between sum of squares indicates the dissimilarity between the clusters. So the idea behind a clustering algorithm is to minimize this value and increase this value. So lower this value, the higher the similarity inside the cluster, and the higher this value, then there'll be greater amount of dissimilarity between the clusters. So this is the entire math behind the k-means algorithm. So is that good? Others? So again, so this is the major part of k-means. So if you understand this, then the rest is a piece of cake.
Just a quick info, guys. If you're interested in becoming a certified data science professional, then check out the data science course offered by Intellipaat. You can find the course link in the description box below. So this brings us to the end of this session. If you have any queries, please do put your comments in the comment box below and we'll reach out to you immediately. Also, do subscribe to our channel to stay updated about our upcoming videos. Thank you for watching this video.